problem 23, part C.
Well, that's my question too.
Okay.
So
I was stuck on finding S sub 4, I think it was. But I don't know what part you're stuck on, Katie.
yeah, no, I mean that's where I got lost.
So would you say 23 part C?
Yes.
A second, let me get my book.
Sure.
I'll let you guys talk to each other for a minute.
Well, this suddenly got awkward.
How are classes from home going for y'all?
So anybody have any live classes?
I don't. I might end up having one.
I have one.
I don't. Yeah, I don't either.
I have one.
Which one is that, Aaron?
That's my ROTC class. It was at 7:45 this morning.
Ooh.
What? Wait, what do you do for ROTC class?
Depends. There's like a whole curriculum you have to go through. But today we basically just talked about current events. So.
Okay. Man, that's early. Wow.
Yeah.
All right. 23C. That's what you're telling me on 8.2?
Yes.
Oh man, hang on a second, everyone. This is gonna seem sort of weird, but this is just what I have to do. I have to join. Oops. I have to join the meeting twice. Okay, so 23C. Oh, that's just the one where you're trying to color the vertices of that thing?
Yes. So I decided to do it the inclusion-exclusion way rather than the Alona way. And it worked for most of them. But I was trying to keep a consistent method going. And for finding S sub 4, I was struggling with that one a bit.
Okay, so all right. Yeah. Yeah, so a lot of those so you made a set for each one of the edges probably, right? Is that what you did? Or yeah, right, you made a set for each one of the edges. Yeah.
Yes, like we did in the example in class.
Okay, so let me do this. Yeah, one thing that you can do that might be helpful is basically you have a lot of symmetry. Okay, basically you have a lot of symmetry with these edges. You guys can see my iPad, right?
Yes.
Okay. Ilona, are you in here right now?
Yeah.
Oh, why don't I see you? It's all right.
Probably have to click the down.
Oh, there you are. There you are. Hey.
Hey.
But now Elise is kicked off. So we have this. Yeah. And so let's let this edge be edge number. Now what I'm going to try to do is I'm going to try to take advantage of some like symmetry. Okay. So like this edge right here and this edge right here are like symmetrically the same. Do you know what I'm saying? Like they literally play the same role in the graph. Like as far as we're concerned, symmetrically the same. Do you see some other edges that are basically symmetrically the same? Well, how about this edge right here and this edge right here, right? Those two are symmetrically the same, 3 and 4, right? So 1 and 2 are symmetrically the same, 3 and 4 are symmetrically the same. This edge and this edge are symmetrically the same. Okay. So 5 and 6 kind of, are symmetrically the same. And then this edge right here is symmetrically the same. Yeah.
Okay.
And how do you define like the AIs? What's AI?
So I said that A sub I is the number of possible colorings such that, let's see, I'm trying to get the wording exactly correct here. Okay, so I did E sub i's off of the example in class.
Oh, okay.
But it doesn't matter. The set of colorings where the vertices get the same color.
Where, oh, okay.
Where the vertices connected by edge I get the same color.
Edge I has same color on both sides, right?
Right.
Okay, so both vertices on each side have the same color.
Mhm.
Great. So what do we want? Don't we want the size of not E1 and all the way up through not E7 or something? Yes.
Yes.
Yeah. So then, okay, so what's the size of the universe here? The size of the universe is equal to what?
Into the fifth, since there are n color choices and we have 5 vertices colors.
Yeah, yeah. Into the fifth. Okay, minus, now we had all those like paired, we had all those paired edges, right?
Right.
So into the fifth minus, so like, I feel like, so there's 7 situations. So what is it? So, I mean, like the 1, 2 situation that we had. So minus, let's do 2 times the size of E1 minus 2 times the size of E3. Why am I grouping those together? Minus 2 times the size of E5 minus the size of E6 or size of E7. How do I know I could just multiply the size of E1, E3, E5, and E5 by 2 and just ignore 2, 4, and 6?
I'm trying to remember the diagram. I didn't write it down.
Well, here, I'll put it up there for you. I mean, I made edge 1 and 2 totally like symmetrical with one another, yes?
Yes.
Okay, and I made 3 and 4 totally symmetrical with one another. I made 5 and 6 totally symmetrical with one another, and then 7's kind of this anomalous edge, right?
Right.
Does that make sense?
Yes.
So is it clear that the size of E1 and E2 have to be the same, right?
Because they are related to the graph in the same way.
Yes. Yeah, so I might as well just roll those into, that's why I just said, well, minus E1 minus E2, well, that's just going to be twice whatever E1 was, right? And of course, that's not all. I mean, I then have to add things back in, right? So, plus, etc. So like, what is S1? S1 is twice E1 plus twice E2. So this stuff right here that I'm subtracting, right? This is the same as minus S1, okay?
Okay.
So what is the size of E1? What is the size of E1?
Is that going to be into the fourth?
Yes. Okay. And then while we're in here, what's the size of E3? Oh man, is this just going to be pretty simple? So with the size of E3, what's that going to be?
Aren't they all into the fourth?
Yeah, I think they probably are. Okay. So S1, I mean, yeah, they're all just into the fourth. So how many so it's just 7 times into the fourth, right? Okay. And then what about S2? Was that the one that you were kind of working on?
It was actually S to the fourth. So if you
Oh,
look at the
S4.
solution, if you look at the solution in the back of the book, I think they use a different way of thinking about it. But yes, for finding the S sub 4 term by their methods, I was a little confused.
What did you do for S2, Logan?
So for S2, I didn't think to use the symmetries in that way. I was just looking at the general shape of it and noticed that there are. Wait, I'm trying to remember which was the right thing I wrote down and which was the wrong. I messed this up when I first did it. Okay, so I just noticed that for any three edges we pick, or for any 2 edges we pick, there are always 3 colorings we would need to make.
Well, but what about, okay, so hang on. So for S2, we're intersecting 2 edges, right?
Right.
Is it the case? Okay, so either it's going to be kind of like, like this edge and this edge, and I would color those things the same, right? The vertices on there the same.
Right.
So what would that give me? N times N,
Yes.
N cubed? Or what's the other possibility I could have?
They're not adjacent.
Right. And there's a few situations where that arise, but does that really change anything?
It doesn't.
So if I did this and like this, if I did edge 1 and edge 7, then I would have N choices here, N choices at 1, N choices at 7, and then I would have like N choices for that remaining vertex. So it would be N cubed, yeah?
Right.
What do we get for S2?
7 choose 2 times into the third. Because we're picking any 2 of those
S3?
edges.
What'd you get for S3?
Okay, so for S3, I noticed that there are 3 subtriangles in the diagram. And if the edges we pick can or make up any one of those 3 subtriangles, then we have 3 choices. So we have so that would be 3 times into the third. And then everything else is going to be requiring 2 colorings. And so the way the book notates that is they say 7 choose 3 minus 3 times N squared. And they add those 2 quantities together.
Okay, so what you're saying is if you're doing 3 edges, you're either going to have a triangle or what? You're either going to have a triangle. I mean, you could have a triangle, or you could have like a little path of 3 edges. Yes, is that true? I mean, it looks to me like you could have a triangle like this, right?
Mm-hmm.
Or you could have a situation like this. Yeah?
Right.
Or you could have a situation like this. Yes? And what else could you have? I guess you could have a situation like this. and then just have an edge out by its lonesome, yeah? Or sorry, this and this, right? So you have a path of 2 edges like this, and then you
Or
have,
you could have 3 totally disconnected edges as well.
okay, where does that happen?
Wait,
Could that be accomplished?
oh no, I was looking at it wrong.
I think you could have 2 edges connected and then one off by itself, yes?
Yeah.
Right? So what about this triangle situation? What do those contribute? What do the triangle ones contribute?
Those contribute. There are 3 triangles, so 3 ways that can happen, and then each one is in to the third.
Yeah, n cubed. Okay. What
Mhm.
about a situation like this where I have a path of 3 edges?
Then that'll account for 4 of the 5 vertices, so you'll have n squared.
Yeah, these are n squareds. What about the little cherry pit, the cherry, what about the cherries?
So it would also do the same. It would contribute 4 vertices. So you have
Yeah,
n squared.
n squared, yeah. What about the 2 path and then the single isolated edge?
And that should take into account all 5,
Yeah,
right?
what does that
So it
mean?
should be n.
Well, I don't think so. No. So, I mean, I would just have to pick, that takes into account all 5 vertices, yes? Wouldn't I just
Right.
put a 1 color on the 2 edges and then 1 color on the isolated edge?
Oh, that's right, because they're not connected.
Right. So wouldn't that just be n squared also?
Yes.
Right. So you have n squared, you have n squared, and you have n squared, right? So what's the only one that's like different from the other ones?
The n cubed.
Yeah,
thing.
the triangles. That's exactly right. So yeah, I think I believe what they said,
Okay.
what you were saying. So basically, they said 7. Oh man, what in the world did I just do? So you said 7 choose 3. How many triangles are there?
3.
Minus 3. There's going to be that many n squareds, yes?
Right.
Plus how many n cubes?
3.
Okay. And then was S4 the thing that that you were trying to ask about?
Yes. That was the one I was asking about.
Okay, so let's look at this. S4. Okay, let me draw the picture. Right? Well, 4 edges. Well, is there any situation? It seems like the only situation I'm going to have that's not going to involve everything is a triangle with a little edge dangling off. Okay, so what I'm thinking of is there's these situations where you have the triangle and then you just have an edge kind of dangling off like this. Yeah?
Mm-hmm.
What do little configurations like that contribute?
N squared.
N squared.
Okay, I think and think about it. All the other configurations, if I swing an edge out of that triangle, unless I try to create another triangle with the other vertex that's the swinging edge, then I'm going to incorporate that 5th vertex. Does that make sense? So like think about this edge right here. If I were to swing that off, to get another vertex that's not one of these, then I would have incorporated like a 5th vertex, and therefore those would all contribute n.
Yes.
So I think all others, what do all others contribute? All others contribute, what do they contribute?
The n.
N. All right, so how many,
Well, there is another case.
what's another case?
Um, if you go back to the numbered edges, like 1, 4, 5, 7.
Yeah, if you take the exterior of any two
1,
adjacent.
4, 5. Oh, nice.
Or I think if you have 1, 3, 5, and 6.
Oh, that isolated thing, that will be n squared also. Okay. Blah, 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 blah. I have to, or maybe I should erase this. Okay. So that's n squared. What are some of the other ones? So hang on, oh man, this thing's all messed up. Let me redraw the configurations. So I could have this. Something like that is going to contribute n squared. What else could you have? The four edges could do this with each other. And what's that going to contribute?
And then square.
What other situation could we have? We could have a triangle and an isolated edge. Yeah? Somebody said that. What's that going to contribute?
N squared.
What? And I think all other situations, what are all other situations going to contribute?
Will that be n?
Yeah, I think all other situations will have all 5 vertices, yes? Okay, so all others n. Okay. Yeah. Well, how many triangle edge thingies do I have? How many of these guys right here?
10.
10?
I think so.
What exactly is the best way to go about counting these?
Well, probably like, okay, you start with this leftmost triangle. Okay, how many little isolated edges can I append onto that?
3.
3. Okay, so there's 3 plus, and then I move on to the next triangle, which would be this guy right here. Yeah. How many edges can I append onto that thing?
Before?
4.
4. And then of course this triangle over here is just totally symmetrical to the one over on the left. Correct?
All right.
1, 2, 3 possible things over there. Okay. How many triangle isolated edge situations are there?
2.
There's just 2. Yes. Right? There's the leftmost triangle with edge 6, and there's the rightmost triangle with edge 5. So there's 2 of these. Okay. How many of the square situations are there? So I have 2 of those. I have 3 plus 4 plus 3 of these. How many of the little square situations are there?
Just
2.
2.
Is there just 2?
I believe so.
Yeah, I think that's probably right. Yeah, there's just 2 of those. Okay, so all total, what do we have? 14? 14 of those things? Yes.
Right.
Plus, Well, what are we going to do? Just 7 choose 4 minus 14? All other situations? And
Mhm.
that's going to be multiplied by
Okay.
n.
Okay.
Now, what about S5? I think, is S5, I mean, what's going on here? Okay. What about S5? I don't think anything you do. Ooh, wait a minute. Wait a minute.
In the last one in S4, we had
Uh-huh.
the circuit with length 4. If you just do like the diagonal across, and you
Yeah,
still
that's
have
what
that other one.
I was just thinking about that. So things that look like this. Yeah. How many of those are there?
2, I think.
Yeah, there's 2. So these guys contribute an n squared, and there are 2 of those. Okay. And what does everything else contribute?
In.
Yeah. 2n squared plus 7 choose 5 minus 2 times n. And I think once we get to 6 edges, what? What do you think's true about that?
All vertices will be reached because there's always at
Yeah,
least
so
2
that's
edges
just
going into every vertex.
7 choose 6 times n. Okay, and then the S7. What is that?
7 choose 7 times in.
Yeah, yeah, yeah. So man, that's amazing. What does that polynomial end up being? Is that the right answer, by the way?
I think so. That's what I got.
Yes.
Okay. I got to get out of here. Hang on. I'm stuck. Come on. Yeah. Okay, there we go.
Okay. Thank you very much.
Can we check this though? So can you guys read it off to me?
Wait, the simplified version or the non-simplified version?
The non-simplified one. So it was like n to the 5th minus what?
7 n to the 4th, or 7 choose 1 n to the 4th.
7 times n to the 4th plus
7 choose n,
what
or
was it?
7 choose 2 n cubed, or 21 n cubed.
Okay. C 7 2. Those were all just n cubes.
Yeah. And then when you get to S3, that's when
Oh.
it splits.
Yeah, minus. Okay, this is where it gets interesting, right? So
Yeah, so sorry.
go ahead.
We had the quantity and then 3n cubed plus 7 choose 3 minus 3 n squared.
Minus 3n cubed minus, and you said it was 7 choose 3. And I had to take away 3, right? And that was in what? Into the,
N squared.
okay, plus,
And then in S4, you had plus 14n squared plus 7 choose 4 minus 14n.
7 choose 4 minus 14 times n. Okay. And then it was minus, did we have some special things going on here?
Yeah, 2n squared. And the rest, and 7 choose 5 minus 2 was just n terms.
Minus 7 choose, Was it 7 choose 5?
Mm-hmm. We're in S5.
Minus 2 in, right? And then what was the last? Or no, we're not done. So it's plus 7 choose 6, which is just 7 times n, right? And then it was minus n. Is that
Do we
right?
have to do we have to include S7? Oh yeah, you did. Minus n.
Yeah, minus n. Okay. The moment of truth. Wait, did I even share this? Sorry, guys. I'm sitting here talking and not even sharing what I'm typing. Jeez. Okay. Here. I typed it in here. Is that so? Into the 5th minus 7 into the 4th plus 18 into the cube minus 20 n squared plus 8n. Is that the answer?
In the
Look.
back of the book, they actually gave it in the unsimplified form.
Oh, okay. But was this the unsimplified form they gave it in?
I'm looking at the back of the book right now, and it says in part C, end of the 5th minus 7 choose 1 end of the 4th plus
here,
7 choose.
All right. All right. So Wolfram alpha. Okay. So say again. Into the 5th.
Yeah, end of the 5th minus 7 choose 1 end of the 4th.
Well, 7 into the 4th plus
7 choose 2 n cubed.
okay.
Minus, and then there's a quantity because it's an S3, so the minus would distribute through, but 7 choose 3 minus 3n squared plus 3n cubed.
Minus 3 all times n squared. Minus what? 3 n cubed.
Mm-hmm. Yeah, it
3n
looks
cubed.
basically the same.
Huh?
It looks basically the same as what we had.
Okay, so far. Yeah.
And then an S4, 7 choose 4 minus 14 times n plus 14n squared.
Oh, is that what they have?
Yeah,
Oh man, that's exactly what we have.
yeah.
Yeah. So why am I even typing this in here?
For sure.
It's the same, right?
Yes.
Okay. Okay. It looks exactly like this. And they have minus 2 n squared in there, Aaron?
They do in S5.
Okay, and then a minus quantity 7 choose 5 minus 2 times n
Yes.
plus 7n minus n.
Yep.
All right. Hey, the back of the book is infallible. So, all right. So hey, Ilona, are you still in here?
Yeah,
What did you? How did you do it?
I did it like the vertex method.
Right.
So yeah, for part C.
There's only like 2 cases, right?
Yeah.
And
Yep.
what'd
Let
you
me
get?
pull- Yeah, hang on, let me. Okay, so I kind of like. Here, let me draw a picture of how I labeled.
And I talked about this in office hours one day, didn't I? Like Ellie asked me about it, I think.
Yes.
Yeah.
And what did I told her to split it up into, it was like n times n minus 1 quantity.
I don't know if you can see that. This is kind of like how I labeled my figure, because then I just like use that in my talk. I don't know.
Okay, so it was n times n minus 1 squared.
Hmm. So
That's like the first, oh, wait a minute. No. That was a different problem. I'm sorry.
yeah.
Okay, so let me stop sharing this and let me pin you to the screen here.
Oh, okay. I just have like my overleaf pulled up so I can just, I guess, like kind of look at it.
Okay, so what was it?
Okay, so here's my, I don't know if you see my drawing.
Yep.
Okay,
So it's
Cool.
minus 7 plus 18 minus 20 plus 8. 7, 18, 28. 7, 18, 28. 7, 18, 8.
Yeah. Oh, I wrote it at the top also so that we can look back. So anyway, so then
Oh man, that's right. Cool. Okay, so let's see your, how did you do it? Right.
okay, so if you label it like that, I said, so first, when you look at the figure, you can choose the color of A first. So you
Uh-huh.
have N available options for that. And then next I chose the color of B. And it can't be the same color, so there's N minus 1 options.
Can you hold up your picture so I can see what B is?
Yeah. Yeah, I'll just like.
So you chose
so-
A. A is just that little 2, that vertex 2 thing. So N options, then N
Yep.
1 for B.
Yeah, N minus 1 here. And then since C is right next to B, but it's also next to A,
Yep,
it can't
yep,
be either of these colors. So I picked that one next. And so you have N minus 2 options.
yep, yep.
And yep. And so then for next, I chose D.
But that's a triangle as well.
Yeah. So yep. Similarly, you also have N minus 2 options here because you're connected to 2 vertices.
Yeah.
So there's N minus 2 again. And
Uh-huh.
then E is next, and that's like the same situation. So you wind up with N times N minus 1 times N minus 2 cubed.
Yes. Yeah.
So,
Yes.
and it comes out, I think, the same.
Right. That I see it, and that is that's great.
Ilona, could you read off that final result one more time? N times N.
I'm gonna put it in right here.
Okay.
Yeah.
So
So
it was N
Times N
N
minus
times,
1.
and what she did is she started out with the vertex way out to the right, and she said, okay, the thing next to it, there are N minus 1 choices, and then she completed the triangle, the first triangle, in N minus 2 ways. And then she proceeded to the next triangle vertex, and she's going to have N minus 2 options there because that's part of a triangle, yes? And you've already chosen 2 colors. And then what's the, and then finally the last vertex is also part of a triangle, so that's going to be N minus 2 options also. Yeah? If you expand that, let's see what happens. Boom. There it is. Amazing. Has to be right. I think that's pretty cool when it works out like that. The hard way and the easy way. There it is. Yeah. I'll unpin Ilona so that she's not, although that was glorious. So you deserve your moment of fame here. Okay. Yeah. Okay. What else? Other questions?
So it doesn't matter which way we approach that one, like when we're doing that one.
Oh, I don't think so. No.
Okay.
I mean, I think it's pretty clear that setting it up with inclusion exclusion is harder, right?
Yep.
But it works.
Mhm.
Right? But you do have to do a fair amount of thinking in each one of the cases to make sure you're not missing something. Sort of comforting that it worked, though. What else?
Well, I had a question on 25 Part B. I know you've covered it at length in other videos. It's just a really short question. But when you look at the formula for derangement, like D sub n,
Yeah.
maybe I was thinking about it like wrong or too complicated or whatever. But like when you think about D sub n as D sub n minus 1, do you just take just the n and think about that as n minus 1, or do you like decrement the k's as well?
So I'm not,
Maybe
what are you saying?
I don't know. I was struggling to just see the connection you did last time. Like when you got through all of that stuff and when you did that little trick at the end to like make it into instead of d sub n minus 2, change it to d sub n minus 1. I was struggling to see the
Oh,
connection between that and d sub n minus 1.
yeah. So okay, yeah, right. So I mean, the point was like I was missing a summand, right? I was sort of missing. I mean, I think what I had was, hang on a sec. Let me go in here and I'll share this. "30 pages, amazing." Okay, and they're all full. Look at that. Isn't that great? Woo. Okay. So let's see. So I had, what was it? It was like n factorial times, was it 1 over 0 factorial
Mm-hmm.
minus 1 over 1 factorial
Right.
plus 1 over 2 factorial minus dot, dot, dot. And it was plus, what was the last thing that I had before I,
Negative 1 to the n minus 1.
negative 1 to the n minus 1 over,
1 over n minus 1 factorial.
right? And but this, because n factorial is just n times n minus 1 factorial, right? This is really the formula for n times, right? If you go look at that formula for the number of derangements, that's just n times d sub n minus 1, right?
Mm-hmm.
And on the other one was like, wasn't the other one n minus 1 factorial 1 over 0 factorial minus 1 over 1 factorial plus, etc.
Mm-hmm.
plus, and it was minus 1 to the what?
Negative n minus 2.
Yeah, over n minus 2
Right.
factorial, close parentheses. And what we noticed was, okay, this is like, since this thing is like n minus 1 times n minus 2 factorial, then all this junk right here, right, this stuff right here, that's dn minus 2.
Mm-hmm.
So when we add those, so if we added those two things together, we would end up with n times d sub n minus 1 plus n minus 1, oh man, times d sub n minus 2. And that wasn't what we wanted. We wanted to see dn plus dn minus 1, right?
Right.
And so my thought was, well, for crying out loud, we're missing something. Why don't I just straight up add, minus 1 to the n over n factorial here? And what would I add down here?
Minus 1 to the n minus 1.
Over n minus 1 factorial.
Mm-hmm.
And miraculously, what happens if I distribute the n minus 1 factorial and the n factorial? I end up with minus 1 to the n plus minus 1 to the n minus 1, and those are of opposite sign, so they cancel.
Right.
That makes sense? So
Yeah.
what you end up showing is that this thing is actually equal to dn plus dn minus 1.
Okay.
I mean, it's kind of an interesting little trick, but they told us what we wanted, right? They said it should be dn plus dn minus 1, and so that's what we were kind of working toward. I think that's amazing. That, man, I'm gonna have to think about. So this identity fascinates me. the fact that, what was it, n times dn minus 1 plus n minus 1 times dn minus 2, the fact that that equals dn plus dn minus 1.
Right.
Wow. I don't have any intuition behind why that would be true, but there's got to be some kind of reason or rationale why that's true. So that's something for me to think about later on for sure. Or for you. So did you have a specific question on that, Aaron, other than,
No, I think you answered it.
okay.
I in the last video, I don't know like what it was. Maybe it was just because you were running out of space on the whiteboard and you're like writing up there or whatever. But I got a little confused. But
Yeah,
that was
does
it.
it make sense what I did?
Yeah, it does.
Yeah. Okay. Well, what else? Hey, look at number 38. You see it?
An 8.2.
Yeah, yeah. Here, let me go back in here. Yeah, 38 says to show something. It says to show that dn is equal to n minus 1 times the quantity dn minus 1 plus dn minus 2. Isn't that equivalent to this thing up here? Like, I think if I moved dn minus 1 over to there, how many dn minus 1s would I have left over? I had n dn minus 1s, right? And I subtract 1 over, aren't I going to have n minus 1 times dn minus 1?
Mhm.
Right, so number 38 is kind of riffing on this other identity that we actually stumbled upon accidentally. Okay. And it turns out you can write down an interesting identity. Like part B looks pretty interesting to me. So anyways, that is something else that we get for free. I didn't assign number 30, did I, or 38, did I? No. Okay. What else? Anything else?
I had a question. So on number 20, I was asking about the intersections, and you were saying that like if you were to look at like the intersections of those cases that it would be like negligible.
Yeah.
Okay. So you just don't even have to like compute them because you get close
It's
enough
just
already.
that one event, AN video, I showed that one event has probability almost 100%. Yeah. I mean, it's 1 minus 1 over n minus 1, right? So like if the permutations were of length 100, then 99% of the drawing sequences would fall into the AN class. Yeah. So there's just no way that any of those other things could be contributing anything that would be meaningful. I mean, you could think it through and show it, but what you're going to end up with is something that's going to 0 as n goes to infinity. You're going to end up with sets whose probability, because remember, you have to divide through by the size of the universe.
Mm-hmm.
The size of the universe, basically E times n minus 1 factorial or something, right? So when you divide by that, it's just going to blast the size of those intersections down to something that's really small and actually tending to 0.
So then does the entire thing tend towards 100%?
Yes, because it contains a sub n, right?
Right, which does that itself.
Yeah, and that by itself already is going to 100%. Yeah. So that's sort of weird. So when you play that game, you are literally almost guaranteed to draw a top card, to pick a number that corresponds to the top card number. And actually, we know for certain that almost 100% of the time, which card is that going to be? Which card is it gonna be?
10th card.
The last card.
Yeah.
The last card. Almost 100% of the time, you're going to go through that drawing sequence and you're going to draw the last card's number when it's on top. I think that's kind of impressive. So yeah, interesting little problem. And they didn't want you to compute this exactly, did they? Right? They said approximate probability.
Yeah.
The answer is
Okay.
it's almost 100%.
Yeah.
Or it's at least 1 minus 1 over the quantity n minus 1. Okay. That's fascinating. Okay. What other questions do you have? Hey, thank you for putting that sheet together, Aaron. I think that will be helpful. I mean, if you guys want to go through and do that and timestamp things and put that in the Google Doc, that'd be a huge help to me. I just don't know if I have.
Yeah, I was afraid that, like, it wasn't necessarily like my expectation that for you to do it. That was like for us, like, oh, like whoever watches the video or who's part of the
Yeah.
session can say, oh, at this time we did this problem.
Yeah.
Okay.
Yeah. I mean, I always kind of I vaguely remember what I've talked about, so I can at least say, oh, like when people email me, I'll say, oh, go watch this one, you know, and I can at least say that. But it's nice to have it kind of documented somewhere as well. That's pretty helpful, I think.
Yeah.
So thanks for doing that.
I had a question on 40. Just more of a terminology thing. When it says at most one void, excuse me, how many ways are there to deal a 6-card hand with at most one void in a suit, meaning that a suit just doesn't appear?
Yeah, a void in a suit means a suit doesn't appear.
Okay.
So like hearts is missing, but it says at most one void. At most one void. So wasn't that one where we had to use the star thing?
Yeah. N sub M star.
Yeah. We did that one. Ellie, didn't you ask me about that? Or was that Ilona? Oh, someone asked me about that. Who asked?
Yeah,
I
that was just more of
remember
a
who asked.
terminology question.
Okay. Yeah. We had to use the star thing because that deals with at least, right? At least. Which you can get that from at most. Yeah. Well, do you guys have anything else? So, I mean, I don't know if you watched the little mini lecture I gave after going through 8.2 number 20 fairly carefully, but being able to write a permutation that is describing some kind of geometric symmetry, it's like taking it and moving it around or something. Being able to write that in its cycle form is going to be critical, okay? So just make sure you understand that before we move on to the next topic. Oh, this is me over here. I forgot. I was like, who is that just has their, it's me. Okay. And actually my name is there as well. So, okay. So being able to write these things in their cycle decomposition is going to be very, very important. Okay. It turns out that just knowing how to write, different symmetries in their cycle decomposition is really the key to counting these, complicated classes of like, okay, how in the world am I going to get 6 from those 16 two-couplings or whatever? That seems like it's going to be impossible, but it turns out it's not. It's going to all come out. It's going to all fall out of doing this cycle decomposition stuff. Okay. So just make sure you fully understand what's going on with that for sure. Okay. What else? Anything else?
This is more like feedback for grades. Like, is there a way we're able to see?
Yeah, I think what I'm gonna probably do, I've been thinking about that. And I've been kind of been falling behind a little bit, but I'll get caught up here pretty quick. I think I'm probably going to I'm going to type it into SpeedGrader. So I'll type comments in SpeedGrader. I'll say, hey, this is awesome. Hey, this is not good. This is why it's not good. I'll probably type it in there for now. And if it gets more complicated than I would like, then what I'll probably do is just make little videos or something. Okay. If there's some general mistake that I see being made, I'll make a video and just post it. And what I'll probably do for the exam is I'll actually solve the exam in a video and just post it. Does that make sense?
That makes sense.
Like going through every exam and making a video for you personally. I'll make a video of the exam being solved completely, and then I'll post that on YouTube. But I will type some comments as well in SpeedGrader. There's a little comment box I can use. Okay. So I think I'll be able to do it. Does that kind of make sense, Aaron?
Yeah, that makes sense.
I think that's as good as it's going to get right now. I mean, I also thought about, so I have some paper copies of some things. I thought about, writing stuff by hand and scanning it and sending it to your email or something. I could do that as well. But we'll see. What else? By the way, I'm not totally sold on the idea of trying to get to progressively finite games. I may actually stop with chapter 9 because my capstone seminar, I don't know how many of you will still be around, but my capstone seminar is on combinatorial games. So what I might do is just not do chapter 10. And the first thing I'll do in my capstone seminar is I'll actually start with progressively finite games. And that'll kind of be the foundation for where the course goes after that. So I would just go through chapter 10 of this book. So I may just end with chapter 9. I haven't totally decided. I may do a couple things at the beginning, but that will alter the schedule a little bit, which seems kind of needful at present. I don't know that I'm going to be able to just blast through to the end at this point because, we've been delaying homework and things like that, trying to get our feet under us a little bit. So chapter 9 is my target right now. Okay, so just be prepared for that. We'll really know chapter 9 well.
On the subject of upcoming homework, Dr. Hammett, I just wanted to double check. Next week, we are indeed doing another round of 8.2 homework, right? I just wanted to double check that wasn't a typo. Okay.
Yes. Isn't that awesome?
It's three homework sets feature 8.2.
Yeah, well, 8.2 is I think 8.2 is the most important chapter in the entire book. I mean, to me, it's that's where you really kind of start to say, oh man, I feel like I know how to count a whole bunch of stuff. The 8.2 is where you start realizing. I think, if I'm not mistaken, I may have assigned every problem to you in 8.2 at some point once we're kind of done. Okay. I might be wrong about that, but they're all really, I think all of them are really good problems. So yes, there's another section of 8.2 homework. You will be inclusion exclusion masters. Okay. What do you have, like a lantern and you there?
Me?
Yeah.
I have a second monitor, so on that one side it's brighter.
No, I'm talking about you actually have a lantern
Oh,
over your right
that's
shoulder.
just the ceiling light.
What? No, the red thing.
Logan, behind your right
Oh,
shoulder.
sorry. Yes. Sorry. My family made a log cabin wall for my bedroom, so
Ah.
What?
nice.
it's actually really cool.
That's amazing.
And then the desk I'm at right now folds up and goes inside of this doorway that they made.
What?
So you open the door and then the desk falls down.
Yeah.
Yeah,
Cool.
it's nifty.
All right. So the next homework set in the syllabus, I doubt it is correct. When is it? It's we're
I think it was
by a
supposed to
week
be
right now.
due Friday, I think.
What's that? It's supposed to be due Friday?
I think so.
Well, I think we're gonna have to cascade that to like okay, so I don't think that would be reasonable. You could
Mm.
try to do that. I would be impressed. But we'll push that one back. Well, should we call it a day?
I think so.
All right. Hang in there. We'll keep on trucking here.
Bye, everybody.
All right, see
See
ya.
ya, guys. Thank you,
Thanks,
Dr.
Dr.
Hammer.
Hammer.
Thanks.
Yeah.
Thank you.